You know, some physicists are perfectly happy to stay in the lab, just exploring the universe through equations. And then there are people like Lawrence Krauss. He's the kind of scientist who wants to grab you by the hand and take you along for the ride, all the way from the bridge of the Starship Enterprise to the very first moments of time itself. So we're going to dive into the mind of a scientist who isn't just asking the biggest questions, but is actually using science fiction to help all of us wrap our heads around the answers. I mean, this is it, right? The ultimate sci-fi dream. Hitting warp speed, zipping across the galaxy. Who hasn't dreamed of that? And it's exactly this kind of question that Krauss just loves to dig into. For him, these wild ideas aren't just fun thought experiments. No, they're gateways. They're a way for us to start understanding the very real, and let's be honest, very weird laws that govern our actual universe. But look, if you're going to talk about things like warp drive or how the entire universe got started, you can't just be a good storyteller. You need some serious scientific street cred. And Krauss's public voice, it's not just about being a great communicator. It's built on a bedrock of really important, groundbreaking scientific work. He really earned his authority. Okay, check out the dates here, because the timing is what makes this so fascinating. Back in 1915, Einstein cooks up this thing called the cosmological constant because his equations kept telling him the universe was expanding, and he didn't like that. He later called it his biggest blunder. For pretty much the rest of the century, most physicists agreed. But then, in 1995, years before anyone had proof, Krauss and a colleague published a paper basically saying, hey, we think Einstein's blunder's actually real. 3 years later, in 1998, astronomers point their telescopes at distant supernova and bam, they prove it. The universe's expansion is speeding up. Krauss was right. And that prediction, that's the scientific capital he built his entire public platform on. So what even is this cosmological constant? Well, today we've got a much cooler name for it, dark energy. It's this mysterious energy that's woven into the very fabric of empty space. And it's not some small thing. We're talking about something that makes up almost 70% of everything in the entire universe. It's the invisible force that's pushing everything apart faster and faster. And Krauss helped drag that idea back into the spotlight before we even knew it was there. All right, so you've made this huge prediction that turned out to be right. You have all this scientific credibility. What do you do with it? Well, if you're Lawrence Krauss, you write a book called The Physics of Star Trek. You take that hard-earned authority in cosmology and use one of the most beloved sci-fi shows ever to translate these incredibly complex, abstract ideas for pretty much everyone. And see, for Krauss, Star Trek isn't just make-believe. It's a playground for the imagination. It's a way to push up against the very boundaries of what physics tells us is possible versus what's impossible, or what's just really, really, really unlikely. It's his favorite tool for asking, yeah, but what if? So let's take a look at warp drive. Step 1 is the big roadblock, Einstein's special relativity. It's basically the ultimate cosmic speed limit. Nothing with mass can hit the speed of light, period. But then there's step 2. His general relativity is a bit more flexible. It tells us that space-time itself can be bent and stretched. And that opens up a little loophole, which brings us to step 3, the big trick. You create a warp bubble. You literally squish space-time in front of your ship and expand it out behind you. So step 4, the ship itself isn't actually moving faster than light. It's just riding on a wave of space-time. The only problem, to pull it off, you'd need this stuff called exotic matter that has negative energy, something we've never seen and have zero clue how to make. So if warp drive is just implausible, what about the transporter? Beam me up, Scotty. Well, according to Krauss, that's where we leap from implausible to utterly implausible. The problems here aren't just about building the machine. They're baked into the fundamental laws of physics. Let's just start with the data problem. To store the information for a single human being, every single atom, where it is, what it's doing, you'd need 10 to the 28th power kilobytes of data. That number is so big it's almost meaningless. But to put it into perspective, if you tried to download that much information on the fastest internet we have, it would take you several thousand times the current age of the universe. So yeah, you'd be waiting a while. But here's the thing. Even if you could magically solve the data problem, the other issues are way bigger. The amount of energy you'd need to dematerialize a person is like setting off thousands of hydrogen bombs. And then you have the real killer, quantum mechanics. It's called the Heisenberg uncertainty principle, and it basically says you can't know a particle's exact position and its exact momentum at the same time. The very act of scanning someone with enough precision to copy them would literally change them. You just can't make a perfect copy. It's a fundamental no-go. And this is where you really see Krauss's big idea at work. He loves using physics to draw that line between what's fiction and what's reality. But he doesn't just stop at spaceships. He takes all that scientific authority he earned predicting dark energy, and he applies the very same laws of quantum physics to one of the biggest, oldest questions there is. Could our entire universe have come from, well, from nothing? Okay, this slide right here is absolutely crucial to understanding this whole debate. When Krauss talks about the universe coming from nothing, he's using the physicist's definition on the left. It's a quantum vacuum. It's not truly empty, it's the simmering, boiling sea of virtual particles that are constantly popping into and out of existence. But his critics say, hold on, that's not nothing at all. They're thinking of the philosophical definition on the right, absolute non-existence, the total absence of space, time, matter, even the laws of physics. The entire massive argument really just boils down to what you mean when you say the word nothing. And here's Krauss's answer to all that. He basically argues that when people ask why there's a universe, what they're really asking for is a purpose, a reason. And he sees that as a religious question, not a scientific one. For him, science is all about the how. How could this happen? It can describe the physical gears and levers like a quantum vacuum that could lead to a universe. And in his view, that's the only meaningful answer we can ever get. But Krauss's work also takes him to an idea that might be even more mind-bending and, honestly, a lot more humbling. It's a thought experiment that looks not back to the beginning of time, but way, way into the future, to a lonely, empty end. And it makes you question everything we think we know for sure. Just look at these two pictures. On the left, that's our view of the cosmos right now. It's packed with hundreds of billions of galaxies. Beautiful, right? But on the right, that's the predicted view in about 100 billion years. Because of that dark energy pushing everything apart, every single one of those other galaxies will have been shoved beyond our cosmic horizon. They won't just be dim. They'll be gone, vanished from our sight, forever. Now, put yourself in the shoes of a scientist in that future. You build the most powerful telescope imaginable, you look out into space, and all you see is your own galaxy sitting in an endless, empty void. Based on every single piece of data you could possibly collect, you would create a perfect, logical, scientific theory that you live in a tiny, static, island universe. You'd have zero evidence for the Big Bang, no evidence for cosmic expansion, no evidence for dark energy. Your science would be flawless, but your conclusion would be completely and totally wrong. And that's the staggering takeaway here. If the knowledge of those future scientists is completely limited by the cosmic era they happen to be born in, how can we be so sure that ours isn't? It suggests that we might be living in a very special time, a lucky moment in cosmic history where the evidence of our own origins is actually still visible, at least for now. And that leaves us with this really unsettling question, doesn't it? It's a thought that forces you to be incredibly humble. If our whole picture of the universe depends on clues that are literally disappearing over the horizon of time, what vital pieces of the cosmic puzzle might already be gone? What might we be missing right at this very moment, simply because we were born in the wrong cosmic eon to see it?